400 billion stars burn inside the Milky Way alone. Many of them have been burning for longer than our planet has existed, and we now know, confirmed by space telescopes that have stared into the deep, that planets orbit nearly every single one of them. The mathematics of that reality produce a conclusion so clean, so unavoidable, that scientists have wrestled with it for over 70 years. The galaxy should be alive with intelligence, crowded with it, ancient with it. We should be hearing echoes of civilizations that rose and fell before our sun was even born. And yet, across 100,000 light years of spiraling dust and ancient fire, we hear nothing, not a whisper, not a ghost, not a single fingerprint pressed into starlight by any hand other than our own. When we aim every instrument we have ever built into that vast cathedral of darkness, the universe returns one answer, and it returns it every single time. Silence. Not the silence of emptiness, but the silence of something enormous and unresolved. A silence so deep and so total that it has become the greatest unsolved mystery in all of science. Tonight, we trace the shape of that silence, from a question asked between bites of a sandwich at a lunch table in 1950 to sleeping gods waiting patiently at the cold end of time. If this kind of storytelling matters to you, liking and subscribing keeps this journey going, and it means more than you know. Prepare for a journey through cosmic solitude beyond comprehension. We begin. The year was 1950. Summer heat pressed against the windows of Los Alamos National Laboratory in New Mexico. This was the place where scientists had built the first atomic bomb just a few years earlier. The air inside those walls always carried a certain heaviness, a feeling that the people working there understood things most humans never would. On this particular day, a small group of physicists walked to lunch together. Among them was a man named Enrico Fermi. If you have never heard his name, let me paint the picture for you. Fermi was the kind of mind that appears maybe once in a century. He had won the Nobel Prize in physics. He had built the world's first nuclear reactor beneath a football stadium in Chicago. He could do calculations in his head that other scientists needed machines for. His colleagues respected him the way you might respect a storm, with admiration and just a little bit of fear. The conversation that day was light. Someone brought up a cartoon from the newspaper. It showed little aliens stealing trash cans from people's yards. Everyone laughed. The joke led to talk about flying saucers, which were big news at the time. People across America kept reporting strange lights in the sky. The scientists traded theories and laughed some more. It was an easy, relaxed lunch. Nothing special. And then, somewhere between one bite and the next, Fermi went quiet. He looked at the faces around the table, and he asked a question so simple that it sounded almost silly. "Where is everybody?" The table went still. Nobody needed him to explain what he meant. These were physicists. They understood the numbers, and the numbers told a very clear story. Our galaxy, the Milky Way, holds somewhere between 200 billion and 400 billion stars. Many of those stars are far older than our own sun. Some of them have been burning for 10 billion years or more. If even a small number of those stars had planets, and if even a small number of those planets developed life, and if even a fraction of that life became intelligent, then the galaxy should not be empty. It should be crowded, busy, loud. There should be signals flying between star systems. There should be structures so large we could see them from here. There should be evidence, old evidence, ancient evidence, of someone, somewhere, doing something. But there was nothing. No signal, no structure, no shadow, no footprint. It had nothing at all. Fermi did some quick math right there at the table. Even with careful, cautious numbers, the result was the same. Civilizations should exist, many of them. Some should be millions of years older than us. Some should have spread across the entire galaxy by now. A species with even a small head start on humanity, say 1 million years, would have had enough time to visit every star in the Milky Way. They could have done it slowly, with ships far less advanced than anything in science fiction. And 1 million years is nothing compared to the age of the galaxy. You could fit that window into cosmic history more than 10,000 times. So, where were they? Where were the ruins? Where were the old machines drifting through space? Where were the faded radio whispers from civilizations long gone? The sky should have been full of echoes. Instead, it was perfectly, impossibly quiet. That question, asked casually over sandwiches, became one of the most famous unsolved problems in science. It earned a name, the Fermi Paradox. And the word paradox is important here. It does not mean mystery. It does not mean puzzle. It means contradiction. Two things that should not both be true at the same time. The math says intelligent life should be common. The evidence says we are alone. Both cannot be right. And yet, here we are, caught between them. Now here is what makes this paradox cut so deep. It is easy to imagine reasons why one civilization might fail. War could destroy them. Disease could wipe them out. Maybe they poisoned their own planet. Fine. That explains one species. But the Fermi Paradox is not about one species. It is about all of them. Every possible civilization, on every possible world, across billions of years of cosmic history. For the galaxy to be this silent, something must be stopping not just a few of them, but nearly every single one. Think about that. Whatever is responsible for the silence is not a local disaster. It is a universal wall, something so powerful, so consistent, that across an entire galaxy and across billions of years, almost nobody gets through. There is a strange detail about Fermi's question that most people do not know. He actually followed it up with a rough estimate that same afternoon. He told his colleagues he believed the chances were reasonable, that Earth should have been visited by extraterrestrial beings already, perhaps many times over the history of the planet. He was not a dreamer. He was a man who trusted math. And his math told him visitors should have come. The fact that they had not was to him genuinely surprising. Some historians have argued about what exactly Fermi meant that day. Did he mean intelligent life should be common? Or did he mean interstellar travel should be possible? Or was he simply pointing out that our assumptions about both might be wrong? The truth is, we do not have a perfect record of the conversation. What we have is a question that landed like a stone in deep water, and the ripples have not stopped spreading. In the decades since that lunch, hundreds of scientists, philosophers, and thinkers have tried to answer Fermi's question. But they have proposed ideas that range from the logical to the terrifying to the almost unbelievable. Some say life is simply rare, so rare that we might be the only ones. Some say civilizations rise and fall before they ever get the chance to reach out. Some say they are out there right now, hiding in the dark, watching us with eyes we cannot see. And some say the answer is so disturbing that we should pray we never find it. What you need to understand is that this is not just a question about aliens. It is a question about us, about our future, about whether the road ahead leads to the stars or to silence. Every answer to the Fermi Paradox carries a message about what might be waiting for humanity. And some of those messages are beautiful, and some of them are the most frightening ideas the human mind has ever produced. The question was born over lunch. It will follow us for the rest of this journey. And the first tool anyone tried to use to answer it was not a telescope or a spaceship. It was an equation, written on a chalkboard by a man who wanted to organize everything we did not know into a single, elegant line of thought. That equation changed the conversation forever. 10 years after that quiet moment at lunch, another man sat down with a piece of chalk and tried to give the silence a shape. His name was Frank Drake. He was young, sharp, and deeply curious about a question that most serious scientists at the time were afraid to ask out loud. Are we alone? In 1961, Drake organized a small private meeting at the National Radio Astronomy Observatory in Greenbank, West Virginia. The observatory sat in a valley surrounded by mountains, far from city lights and radio noise. It was one of the quietest places on Earth, a fitting spot to discuss the quietest mystery in the universe. Drake had invited a handful of brilliant minds to talk about one enormous problem. How many intelligent civilizations might exist in our galaxy right now? Not in the whole universe, just in our galaxy, the Milky Way alone. The question sounded almost impossible to answer. There were too many unknowns, too many variables, too many places where a guess could go wrong and send the whole calculation flying off a cliff. So, Drake did something clever. Instead of trying to answer the question directly, he broke it into smaller pieces. He wrote a formula on the chalkboard, a chain of multiplications, where each piece represented one thing we would need to know. He never claimed the formula would give a final answer. He called it a way to organize our ignorance, a map not of what we know, but of everything we still need to learn. That formula became known as the Drake equation, and despite being over 60 years old, it remains the starting point for almost every serious conversation about extraterrestrial life. Here is how it works, in plain language. You begin with the number of new stars born in the galaxy each year. We actually know this one fairly well, roughly a few stars per year on average. Then, you multiply by the fraction of those stars that have planets orbiting them. For decades, this number was a pure guess. We had no way to know. But then something extraordinary happened. Space telescopes like Kepler, launched in 2009, began discovering planets by the thousands. And the result shocked everyone. Planets are not rare. They are everywhere. Almost every star in the Milky Way has at least one planet. Some have 5, some have 8. The total number of planets in our galaxy is likely in the trillions. Trillions of worlds, spinning in the dark, most of them never seen by any eye. The next piece of the equation asks how many of those planets could support life. This means being the right distance from their star, not too hot, not too cold, in what scientists call the habitable zone. Current estimates suggest there could be billions of such planets in the Milky Way alone. Billions of places where water could exist as liquid on the surface. Billions of chances for chemistry to become biology. So far, the numbers are generous. The galaxy seems to be overflowing with raw ingredients. But now, the equation moves into darker territory. The next step asks how often life actually begins on a planet where conditions allow it. And here, we hit a wall. We have exactly one example: Earth. Life appeared here roughly 3.8 billion years ago, but we still do not fully understand how. We know it involved simple molecules arranging themselves into something that could copy itself and change over time. Scientists have recreated some of these steps in laboratories, but the full picture, the moment when dead chemistry crossed the line and became alive, remains one of the deepest mysteries in all of biology. Maybe it happens on every suitable planet. Maybe it happens on 1 in a billion. We simply do not know, and that single unknown can change the entire outcome of the equation by orders of magnitude. The next term asks how often life becomes intelligent. Again, one example: us. On Earth, life existed for billions of years as nothing more than single-celled organisms, simple bacteria, floating, dividing, doing very little. It took an almost unbelievable amount of time, and what may have been a freakishly unlikely event, for complex life to appear. Intelligence came even later, and the kind of intelligence that builds telescopes and wonders about the stars. That showed up only in the last sliver of Earth's history. If you compressed the entire life of our planet into a single 24-hour day, human civilization would appear in the final second before midnight. Then, Drake's equation asks one more question, and it might be the most important one of all. How long does a civilization last once it develops technology? Think about that carefully. A species discovers radio waves. It builds telescopes. It splits the atom. And then what? Does it survive for 1,000,000 years and spread across the stars? Or does it destroy itself within a few centuries? Through war, environmental collapse, or something it built that turned against it? We have no data on this. Zero. We are the only technological civilization we know of, and we have only been one for about 100 years. That is not enough time to answer the question. We are still inside the experiment. Here is what makes the Drake equation so powerful and so frustrating at the same time. When you plug in optimistic numbers, when you assume life is common, intelligence appears regularly, and civilizations tend to last. The equation says there should be thousands, maybe tens of thousands of civilizations in the Milky Way right now. The galaxy should be humming with activity, signals bouncing between stars, beacons flashing from distant worlds. There's evidence of engineering on scales we can barely dream of. But when you plug in cautious numbers, when you assume that even one of those steps is extremely rare, the equation can spit out a number close to 1. Just us, alone in the entire galaxy. The difference between a crowded city and an empty graveyard comes down to small changes in variables we cannot yet measure. There is a strange and lesser-known detail about the original Green Bank meeting. One of the attendees was a young scientist named Carl Sagan, who would later become the most famous science communicator of the 20th century. Sagan reportedly left the meeting both inspired and troubled. He spent the rest of his life advocating for the search for extraterrestrial intelligence. But he also understood something that haunted him. The equation did not give comfort. It gave structure to a question that might never have a comfortable answer. Some critics have argued that the Drake equation is not really science. It is more like a thought experiment dressed in mathematical clothing. You can make it say almost anything depending on which numbers you choose. And since we are guessing on most of those numbers, the result is less a calculation and more a mirror, reflecting our hopes and fears back at us. But Drake himself never claimed otherwise. He called it a roadmap, a way to see clearly what we need to learn next. And in that sense, it has been wildly successful. Nearly every major mission in astrobiology, from Kepler to the James Webb Space Telescope, traces its purpose back to one of the terms in Drake's equation. We are slowly, carefully, filling in the blanks he left on that chalkboard over 60 years ago. The equation points in one direction. The ingredients are there. The chances are real. Something should exist out there. And that makes the silence not just strange, but almost painful. Because when you step back even further, when you truly understand how old this galaxy is and how much time the universe has had to fill itself with voices, the emptiness begins to feel less like a mystery and more like a warning written in the dark. Now let us talk about time. Not the kind you feel passing during a slow afternoon. Not the kind measured by clocks on walls or calendars on desks. The kind of time that breaks something inside your brain when you truly try to hold it. Because when you see how old this galaxy really is, when you feel the weight of those billions of years pressing down on Fermi's question, the silence stops being a curiosity. It becomes something closer to a scream. The Milky Way is roughly 13 billion years old. Our own sun, the star that warms your face and grows your food, formed about 4.5 billion years ago. That means the galaxy had been making stars, building planets, and cooking up complex chemistry for more than 8 billion years before Earth even existed. 8 billion years of opportunity. 8 billion years of rolling the dice on world after world after world. And we were not even part of the game yet. Let that settle for a moment. Human civilization, the part where we built cities and wrote things down, has existed for maybe 10,000 years. The technology that lets us send signals into space, radio towers, satellites, telescopes, has existed for about 100 years. 100 years. In cosmic terms, that is not even a heartbeat. It is less than the blink of an eye. If you compressed the entire history of the Milky Way into a single calendar year, with January 1st being the birth of the galaxy, our sun would not appear until late September. Earth would form shortly after. And the entire history of human civilization, every empire, every war, every love letter, and every rocket launch, would fit into the final half second before midnight on December 31st. That is how small we are against the backdrop of deep time. Now imagine something that should keep you staring at the ceiling tonight. What if another civilization got started just 1% earlier than us in the life of the galaxy? 1% does not sound like much, but 1% of 13 billion years is 130 million years. A head start of 130 million years. Try to picture what that means. Think about how far humanity has come in just the last 300 years. We went from riding horses to landing on the moon, from sending letters by ship to bouncing signals off satellites, from candlelight to lasers, from wooden boats to spacecraft that have left our solar system, all of that in 3 centuries. Now stretch that kind of progress across 100 million years. The result is something the human mind simply cannot hold. A species with that kind of head start would not just have visited nearby stars. They would have reshaped the galaxy itself. They could have wrapped entire stars in energy-collecting structures. They could have moved planets. They could have left behind traces visible from millions of light years away. And 130 million years is a modest head start. Some stars in the Milky Way are nearly as old as the galaxy itself. Planets formed around those stars billions of years before our world was even a cloud of dust. If life appeared on any of those early worlds and somehow developed intelligence, those civilizations had so much time that the numbers lose all meaning. They could have risen, fallen, risen again, and spread to 1 million worlds, all before our solar system was born. There is a concept scientists use to sharpen this point. It is called the colonization timescale. Researchers have calculated that even with slow ships, vessels traveling at just a tiny fraction of the speed of light, a single civilization could colonize the entire Milky Way in somewhere between 1 million and 10 million years. That sounds enormous to a human ear, but hold it against the age of the galaxy. You could fit that colonization window into the Milky Way's history thousands of times over. A civilization that launched its first colony ship 5 billion years ago would have had enough time to settle every star system in the galaxy, to rest for 1 billion years, do it all over again, and still have time left over. This is the part that turns the Fermi Paradox from an interesting thought experiment into something that feels almost personal. We are not asking a casual question about whether aliens might exist somewhere. We are asking why, after billions of years of opportunities across hundreds of billions of stars, we see no trace of anyone. No ancient ruin on any moon. No waste heat radiating from a star wrapped in technology. No drifting machine from a species that vanished ages ago. No mark of any kind, from any era, anywhere. The universe had the time. It had the ingredients. It had more chances than we can count. And yet, when we look out into the dark, the cosmos appears untouched, fresh, as if no one has ever been here before. There is a strange detail that deepens this discomfort even further. Scientists have pointed out that you do not even need living travelers to fill the galaxy. You just need machines. In the 1940s, mathematician John von Neumann described a theoretical device that could copy itself. The idea was straightforward. You send one machine to a nearby star system. When it arrives, it gathers raw materials, metals from asteroids, ice from comets, and builds an exact copy of itself. That copy launches toward the next star. The process repeats. Each generation builds more copies. Each copy travels further. The spread is exponential. Even at slow speeds, the math says a single self-replicating machine could have descendants in every star system in the galaxy within a few million years. One machine, one launch, and the galaxy is filled. Any civilization that ever built such a device at any point in the last several billion years should have left behind a web of machines stretching across every corner of the Milky Way. We should be tripping over them. They should be sitting on asteroids in our own solar system, parked on our moon, drifting through the cold space between planets. And yet, as far as we can tell, there is nothing there. Some scientists have suggested that maybe the probes were built and simply broke down over millions of years. Metal corrodes, circuits fail. Given enough time, even the toughest machine turns to dust. But others argue that a truly advanced self-replicating system would be designed to maintain and rebuild itself indefinitely. The whole point is that it keeps going. That is what makes it so effective and so troubling. There is one more idea that adds a final unsettling layer. What if the machines did arrive in our solar system? What if they are here right now, sitting quiet and dormant on some dark rock we have never bothered to examine? Our ability to survey even our own system is shockingly limited. There are millions of objects in the asteroid belt alone, billions more in the outer reaches. A machine the size of a car, powered down and waiting on an asteroid 1 billion miles away, would be completely invisible to us. We would not know it was there unless we went looking, and we have barely started looking. The weight of deep time turns the Fermi Paradox into something almost unbearable. It is not just a question about the present, it is a question about every moment that ever was, every civilization that could have risen, every probe that could have been launched, every signal that could have been sent. The galaxy has had more time than we can hold in our imaginations, and the answer, so far, is silence. Total, perfect, deafening silence. But once, just once, something broke through that silence. For 72 seconds, on a warm summer night in 1977, a telescope in Ohio heard something that still has no explanation. And that brief whisper from the dark changed the search forever. It was a warm August night in 1977. The kind of night where crickets sing and the sky feels close enough to touch. In a field outside Columbus, Ohio, a radio telescope called the Big Ear was doing what it did every night, quietly listening to the cosmos. The telescope was enormous, shaped roughly like a football field, its metal arms stretched wide to catch whispers from deep space. Most nights were boring. The machine recorded the same thing over and over, static, background hum, the soft, meaningless noise of a universe going about its business. Astronomers would review the data printouts each morning, scanning columns of numbers and letters, finding nothing unusual. Night after night after night. Just silence wearing a thin disguise of noise. Then, for exactly 72 seconds, something changed. Here the telescope picked up a signal. It was powerful, far stronger than the background noise around it. It was narrowband, meaning it occupied a very tight slice of the radio spectrum, the kind of clean, focused transmission that nature almost never produces. And it arrived on a frequency that made scientists catch their breath. 1420 megahertz. That number matters because it is the natural emission frequency of hydrogen, the most common element in the universe. For years, researchers had argued that if an intelligent species wanted to send a message across the stars, this would be the logical channel to use. Any civilization that studies the cosmos would know about hydrogen. It would be a universal meeting point, a frequency that says, I understand how the universe works, and I chose this channel on purpose. The signal rose in intensity, hit a peak, and then faded. The pattern matched exactly what you would expect from a source fixed in deep space as the Earth rotated beneath the telescope's beam. It came from the direction of the constellation Sagittarius, far beyond our solar system. It behaved precisely the way a genuine extraterrestrial transmission should behave. A few days later, astronomer Jerry Amon was reviewing the data printout. He was going through columns of characters, each one representing the strength of incoming signals. When his eyes hit one particular sequence, he stopped. The numbers were unlike anything he had seen before. He grabbed a red pen, circled the cluster of characters on the paper, and wrote a single word in the margin. Wow. That word became the signal's name, and it became a legend. Here is why the WOW signal shook the scientific world. It matched nearly every criterion that researchers had outlined for what an alien message might look like. It was narrow in frequency. It came from deep space. It appeared on a scientifically meaningful channel. Its strength towered above the surrounding noise. If you had written a checklist for what to expect from a genuine extraterrestrial broadcast, the WOW signal would have ticked almost every box. But there was one devastating problem. It never came back. Amon and other astronomers pointed the big ear at the same patch of sky dozens of times in the following weeks and months. Other telescopes joined the effort. For years, people kept listening to that exact spot, on that exact frequency, waiting for the voice to speak again. They heard nothing. The signal appeared once, a single shout across the dark, and then vanished completely, as if it had never happened. That single detail is what keeps the WOW signal trapped in the land of the unknown. In science, one observation is never enough. To confirm something is real, you need to see it again. You need to repeat the measurement. You need independent verification. And despite decades of effort, no one has ever detected a second occurrence of the WOW signal. It remains alone, an unrepeated whisper. Over the years, scientists have proposed several natural explanations. Maybe a comet passing through the area released hydrogen gas that mimicked the signal. A study in 2017 suggested two specific comets that were in the region at the time and could potentially explain the burst. But other researchers pushed back hard. They argued the signal was too strong and too clean to come from a comet. The math did not quite work. Another idea blamed interference from Earth-based technology. A satellite reflection, a military transmission, some kind of radio pollution bouncing off something it should not have bounced off. None of these explanations perfectly fit the data. The honest answer, confirmed by the scientific community after nearly 50 years of debate, is simple and maddening. We do not know what caused the WOW signal. We do not know if it was natural or artificial. We do not know if it came from a civilization or from some strange astrophysical process we have not yet identified. It remains the single strongest candidate for a potential extraterrestrial transmission ever recorded, and at the same time, it remains completely unverified. There is a detail about the WOW signal that most people never hear. The Big Ear telescope actually had 2 feed horns, 2 separate receivers that scanned the same strip of sky a few minutes apart. If the signal had been real and persistent, it should have appeared in both receivers. It only appeared in one. That could mean the signal was incredibly brief, lasting only moments. Or it could mean the source turned on and off. Or it could mean something about the geometry of the detection was unusual. No one knows for sure. It is one more thread in a knot that has never been untied. Think about what this means for the Fermi Paradox. Across more than 60 years of searching, across thousands of hours of telescope time, across millions of frequencies scanned, this is the best we have found. One signal, 72 seconds, one word scrawled in red ink, and then nothing ever again. It is like standing in an enormous dark forest, hearing a single twig snap somewhere far away, and then spending the rest of your life listening to perfect silence, never knowing if something was really there or if the wind simply fooled you. There is something almost cruel about it. The one time the universe seemed to answer, it spoke a single syllable and went mute forever. Was it them? Was it nothing? Was it a natural event we simply do not understand yet? Or was it exactly what it looked like? A voice from across the galaxy, reaching out, briefly touching our instruments, and then withdrawing back into the dark for reasons we may never learn. Both possibilities are haunting. If it was a natural event, then the universe can perfectly mimic the signature of intelligence, and our search is even harder than we thought. If it was artificial, if someone really did send that signal, then it means they are out there, or at least they were, and they chose not to speak again. Either they could not, or they decided not to. And we are left standing in the dark, holding a single faded note, wondering if the sender is still alive. After almost half a century, the WOW signal remains exactly what it was on the night Jerry Amon circled those characters with his red pen. A mystery. A beautiful, frustrating, heartbreaking mystery. The loudest silence in the history of science, and it forces us toward a much harder question. If the galaxy has had billions of years to produce civilizations, and if even the best signal we have ever found vanished before we could confirm it, then maybe something is stopping them. Not some of them. All of them. Something enormous. Something nearly impossible to survive. Scientists have given this invisible wall a name, and what it implies about our future is enough to change how you see every star in the sky. Picture a staircase. At the very bottom, there is nothing but dead rock and cold gas. Lifeless chemistry drifting through empty space. At the very top, there is a civilization so powerful it stretches across the stars, building, exploring, leaving marks visible from 1,000,000 light years away. Between those 2 points are dozens of steps, the formation of a stable planet, the appearance of the first simple life, the development of complex cells, multicellular creatures, intelligence, technology, space travel, long-term survival. Each step leads to the next. Each one brings a species closer to becoming something the galaxy can see. Now imagine that somewhere on that staircase, there is one step that is almost impossible to climb. A barrier so deadly, so difficult, and so unlikely to be cleared that nearly every species that attempts it fails. They fall, they vanish, they go silent, and the galaxy never hears from them. That is the great filter. The idea was proposed in 1998 by economist Robin Hanson. He looked at the Fermi Paradox and asked a different kind of question. Instead of wondering where the aliens are, he asked what single barrier could be powerful enough to explain the silence of an entire galaxy across billions of years. His answer was chilling in its simplicity. There must be a wall. Somewhere on the path from dead chemistry to galactic civilization, there is a step that almost nobody survives. The silence is the proof. The empty sky is the evidence. Something is killing them. Not one species, not a few unlucky worlds, but nearly everyone who tries. Here is where this idea becomes deeply personal. Because there are only two possibilities. Either the great filter is behind us, or it is ahead of us. And the difference between those two options is the difference between the most extraordinary luck imaginable and a death sentence we have not yet received. Let us start with hope. If the filter is behind us, it means we have already passed through the hardest part. Somewhere in our distant past, Earth cleared a step so difficult that almost no other planet in the galaxy has managed it. We survived the impossible, and we did not even know it was happening. In this version of the story, we are the winners of a cosmic lottery. The galaxy is silent, not because civilizations keep dying, but because almost none of them ever get started. There are several candidates for where this filter might sit in our past. The first is the origin of life itself. Around 3.8 billion years ago, simple molecules on Earth somehow crossed the line from dead chemistry to living biology. We call this abiogenesis, and we still do not understand how it happened. If this step is extraordinarily rare, if most planets with water and warmth simply sit there, sterile, for billions of years, then the filter might be right at the beginning. Life itself might be the miracle. The second candidate is even stranger. For roughly 2 billion years after life appeared on Earth, nothing much happened. The planet was covered in simple single-celled organisms, bacteria, nothing more. Then, somewhere around 2 billion years ago, something occurred that scientists believe may have only happened once in the entire history of our planet. One cell swallowed another cell. But instead of digesting it, the first cell kept the second one alive inside itself. That captured cell eventually became what we call mitochondria, the tiny engines that power every complex living thing on Earth today. Every animal, every plant, every fungus, all of them trace their energy back to that single ancient merger. Scientists call this event endosymbiosis, and the evidence suggests it may have happened exactly once in 4 billion years of life on Earth. Once. If that merger is the filter, then the galaxy might be covered in planets full of bacteria that will never become anything more. Oceans of simple life, stretching from star to star, with no path forward. Now let us look at the version that should terrify you. If the filter is not behind us, it is ahead. And that means everything we have accomplished so far is ordinary. Life is common. Intelligence is common. Building telescopes and dreaming about the stars is something that thousands of species across the galaxy have already done. And then something destroyed them. Every single one. The same wall, every time, and nobody has ever climbed over it. What could that wall be? The most obvious candidate is nuclear weapons. Humanity split the atom in the 1940s. Within years, we had enough firepower to end our civilization many times over. During the Cold War, we came terrifyingly close to using it. There were moments, real, documented moments, when a single misread radar signal or one nervous officer's hesitation was the only thing standing between the world we know and total annihilation. We survived those moments, barely, and the weapons have not gone anywhere. The clock never stops ticking. Now imagine every intelligent species in the galaxy eventually discovering nuclear energy. The physics is universal. The knowledge is inevitable. If even a small percentage of those species fail the test, that alone could fill a galaxy with silence. Then there is a newer candidate, and it is gaining serious attention. In 2023, astrophysicist Michael Garrett published a paper arguing that artificial intelligence might be the great filter. His reasoning is haunting, and every civilization that reaches a certain level of technology will eventually build machines smarter than itself. The transition happens fast, possibly too fast for any biological species to control. Garrett estimated that the window between a civilization inventing radio technology and losing control to artificial intelligence might be less than 200 years. 200 years. In cosmic terms, that is a flash of lightning. If this is true, then the galaxy could be full of dead worlds where the lights went out almost as soon as they turned on. This is the cruel math of the great filter. If the hard part is behind us, we should celebrate. We are the survivors, the lucky ones, the species that cleared the impossible step. But if the hard part is still ahead, then every discovery that makes life look common is not good news. It is a warning. Every time we find water on another world, every time we detect organic molecules in a distant atmosphere, it means the early steps are easy. And if the early steps are easy, it means the killing blow comes later. It means the thing that silences civilizations has not reached us yet. But it will. We do not know which side of the filter we are on. That uncertainty is the deepest terror of the Fermi Paradox. We stand on the staircase, looking up into darkness, unable to see whether the next step is solid ground or an edge that drops into nothing. And the only clue the universe gives us is the silence itself. A silence so vast and so complete that it might be the loudest warning we have ever received. But perhaps the wall is not a single catastrophic moment. Perhaps it is something quieter, a long list of conditions so specific, so dependent on luck and timing, that most planets simply never check every box. The next part of our journey examines the possibility that Earth itself is the miracle, and that worlds like ours are almost impossibly rare. What if the problem is not that civilizations destroy themselves? What if the problem is that planets like ours almost never exist in the first place? What if Earth is not ordinary at all, but a freak accident? A world so unlikely, so dependent on a chain of lucky events that across hundreds of billions of star systems, almost nothing like it has ever appeared. That is the heart of the rare Earth hypothesis. In the year 2000, paleontologist Peter Ward and astronomer Donald Brownlee published a book that shook the scientific world. They argued that while simple life, bacteria, microbes, basic organisms might be scattered across the galaxy, complex life is extraordinarily rare. Not because of some great catastrophe or invisible hunter, but because the conditions needed to grow complex life require a list of ingredients so specific that most planets will never check every box. And when you see that list, when you truly understand how many things had to go right for you to exist, the silence of the galaxy begins to feel less like a puzzle and more like the only possible outcome. Start with where we are in the galaxy. Our sun sits in what scientists call the galactic habitable zone. This is a narrow ring between the dangerous center and the barren outer edge, too close to the core of the Milky Way, and the radiation from tightly packed stars would sterilize any planet. Supernovae would explode nearby, bathing entire regions in lethal energy. Too far out toward the rim, and there are not enough heavy elements, metals, silicon, or carbon, to build rocky worlds at all. Earth sits in a sweet spot, a thin band in a galaxy of hundreds of billions of stars where conditions are neither too violent nor too empty. Now look at our star. The Sun is a G-type main sequence star. It is stable. It is long-lived. It does not throw deadly tantrums of radiation the way many other stars do. A huge number of stars in the galaxy are red dwarfs, smaller, cooler, and far more common than stars like ours. But planets orbiting red dwarfs tend to be tidally locked, meaning one side permanently faces the star in endless burning daylight, while the other side freezes in eternal night. Building a complex ecosystem on a world like that is incredibly difficult. Our star gives us something most planets never get: a calm, its steady source of energy that has burned reliably for 4.5 billion years. Then there is the planet itself. Earth has a magnetic field. You cannot see it, you cannot feel it, but without it, you would not be alive. This invisible shield deflects charged particles streaming from the sun, the solar wind, that would otherwise strip away our atmosphere molecule by molecule. That is exactly what happened to Mars. Mars once had a thicker atmosphere. It may have had liquid water on its surface, but its core cooled, its magnetic field died, and the solar wind slowly peeled its air away. Today, Mars is a cold, dry wasteland with an atmosphere so thin you could not breathe a single lungful of it. Earth's magnetic field comes from a spinning iron core deep beneath our feet, and that core is still hot, still churning, partly because of an event so violent and so unlikely that it might be one of the rarest things in the entire galaxy. About 4.5 billion years ago, a Mars-sized object scientists call Theia slammed into the young Earth. The collision was catastrophic. It melted much of our planet's surface. It blasted enormous amounts of debris into orbit. That debris eventually came together and formed our moon. But the impact did something else, something that may have been even more important. It reheated Earth's interior, delivered extra radioactive elements that still generate heat today, and may have created the conditions needed for something that makes our planet truly unique: plate tectonics. Earth is the only known planet with active plate tectonics. Its outer shell is cracked into massive slabs that float on a layer of hot, semi-molten rock below. These plates move slowly, just a few inches per year. But over millions of years, they reshape continents, open and close oceans, and drive a process that has kept Earth habitable for billions of years. When volcanoes erupt along plate boundaries, they release carbon dioxide into the atmosphere. That carbon warms the planet. Over time, rain washes the carbon out of the air and into the ocean, where it sinks into the crust. When plates slide beneath each other, a process called subduction, that carbon gets recycled back into the deep Earth. Then, volcanoes release it again. This loop has acted as a thermostat for our planet for billions of years. When Earth gets too cold, volcanic carbon warms it up. When it gets too hot, its weathering pulls carbon out. Without this system, our planet would have either frozen solid or turned into a furnace long ago. Mars does not have plate tectonics. Venus does not have it. Mercury does not have it. Our moon does not have it. A study published in 2024 in Scientific Reports proposed that plate tectonics might itself be one of the most important pieces of the Great Filter. Without it, no carbon recycling. Without carbon recycling, no long-term climate stability. Without stability, no time for complex life to evolve. The researchers traced the origin of Earth's tectonic system back to the Theia impact, that random violent collision that also gave us our moon. A 2025 study reinforced this, is arguing that the Theia collision provided the earliest evidence of subduction just a few 100 million years after the impact itself. Plate tectonics may not be something that develops naturally on most rocky planets. It may require a freak accident of exactly the right size, at exactly the right speed, at exactly the right moment in a planet's history. And the list goes on. Earth has a large moon that stabilizes the tilt of its axis, keeping seasons relatively mild over long periods. Without that stability, the climate would swing wildly, making it nearly impossible for complex life to gain a foothold. Earth also has Jupiter, a giant planet sitting further out in our solar system, using its enormous gravity to catch or deflect asteroids and comets that would otherwise pummel our world. Without Jupiter, catastrophic impacts on Earth would be far more frequent. And then there was the asteroid that killed the dinosaurs 66 million years ago, a random event that opened the door for mammals to rise, for primates to evolve, for intelligence to emerge. Stack all of these conditions together: the right galaxy, the right position in that galaxy, the right type of star, a rocky planet in the habitable zone, a magnetic field, plate tectonics, a large stabilizing moon, a gas giant protector, liquid water on the surface, billions of years of relative stability. Each condition might be common on its own, but needing all of them at once, on the same world, in the same era, is like rolling a dozen dice and needing every single one to land on 6. Maybe the galaxy is not empty because civilizations destroy themselves. Maybe it is empty because almost no planet is lucky enough to grow one. And maybe Earth is not ordinary at all. Maybe it is a masterpiece painted by accidents, each brushstroke so unlikely that the canvas should have stayed blank. But even this explanation may not be strange enough, because some ideas go darker still, into a place where the silence is not about luck or physics, but about strategy, fear, and the cold mathematics of survival in a universe where being discovered might be the most dangerous thing that can happen to you. Everything we have explored so far assumes the galaxy is empty, that no one is out there, that the silence is real because there is genuinely nothing making noise. But what if that assumption is completely wrong? What if the galaxy is full of civilizations, thousands of them, maybe millions, and every single one is hiding? Not because they are shy, not because they lack the technology to speak, but because they understand something terrible about the universe, something we have not yet learned. The penalty for being discovered is death. That is the dark forest theory. The concept was described most famously by Chinese science fiction author Liu Cixin in his novel The Dark Forest, published in 2008. But the idea beneath the story is not fiction, and it is built on game theory, the branch of mathematics that studies decisions between competing players. And the conclusion it reaches is one of the most haunting ideas ever applied to the Fermi Paradox. Here is the picture. Imagine the galaxy as a vast, dark forest at night. Every civilization is a hunter moving through the trees. They are armed, they are afraid, and they know that somewhere out there, other hunters are doing the same thing. The forest is silent, not because it is empty, but because every hunter who makes noise gets killed. Survival belongs to those who stay quiet. Discovery belongs to the dead. The theory rests on two simple starting points. First, survival is the primary goal of every civilization. Second, resources in the universe are limited. From those two ideas, the logic unfolds with cold, mechanical precision. When one civilization discovers another, it faces a problem it cannot solve. It cannot know the other's intentions. Maybe the other species is peaceful. Maybe it is not. There is no way to be certain. Communication across interstellar distances takes years or decades. Trust cannot be built quickly, and even if the other civilization seems harmless today, it might become powerful tomorrow. technology changes. A weak neighbor now could become a deadly threat in 1,000 years, or 100, or 10. The safest move, according to the mathematics, is to strike first, destroy the other civilization before it has a chance to grow. And if every civilization in the galaxy reaches the same conclusion through the same logic, the result is a universe where everyone hides, because revealing yourself means inviting annihilation. This is not a fringe idea whispered by conspiracy theorists. Researchers at the Search for Extraterrestrial Intelligence Institute have acknowledged that the logic is not implausible. Game theorists have modeled the scenario using formal decision frameworks, and the results support the basic structure. When you cannot verify another player's intentions, and when the cost of being wrong is extinction, silence becomes the dominant strategy. Speaking is gambling with everything. Hiding is free. Let us walk through the math more carefully, because this is where the chill deepens. Imagine two species. Call them Civilization A and Civilization B. They have just detected each other across the stars. Each one has two choices: communicate peacefully or launch a preemptive strike. If both cooperate, both benefit. They share knowledge, resources, security. That is the best outcome for everyone. If one cooperates and the other attacks, the cooperative one is destroyed, while the attacker gains everything. If both attack, both suffer devastating losses. This is a version of the classic prisoner's dilemma. And in the prisoner's dilemma, when the stakes are extinction and trust is impossible, the rational choice is always betrayal. Always. Not because the players are evil, but because the math leaves no room for hope. 3 brutal facts make cosmic trust nearly impossible. First, communication is slow. Signals between stars take years or decades to travel. You cannot have a real-time conversation. You cannot read body language. You cannot negotiate the way 2 humans can across a table. Second, intentions are unknowable. A civilization that seems peaceful might be quietly building weapons. A friendly message could be a trick. There is no way to verify what another species truly wants, especially when their biology, psychology, and culture might be completely alien to yours. Third, technology changes over time. Even if Civilization B is weaker today, it could surpass Civilization A in a century. The longer you wait, the more dangerous a potential rival becomes. These 3 factors create what game theorists call a chain of suspicion. You do not know what they think. They do not know what you think. And both of you know that the other is running the same calculation. The result is an infinite loop of distrust that mathematically favors one strategy above all others: silence, and if discovered, destruction. Some researchers have expanded this model to include many civilizations at once. The result is even darker. In a galaxy with many players, any civilization that reveals the location of another essentially paints a target on them. You do not even need to fire the shot yourself. You just need to broadcast where someone is and let the forest do the rest. Location becomes a weapon. Coordinates become a death sentence. Now think about what humanity has done. We have been broadcasting radio signals into space for over a century. In 1974, we sent the Arecibo message, a deliberate, focused transmission aimed directly at a star cluster 25,000 light-years away. We launched the Voyager probes carrying golden records with our location, images of our biology, samples of our music. We have been lighting fires in the dark forest for decades. If the dark forest theory is correct, that was a catastrophic mistake. We have been screaming our coordinates into a universe where the price of being heard is annihilation. Our radio signals have already traveled over 100 light-years into space. Any civilization within that expanding bubble now knows we are here. Some experts push back on this. Astrophysicist Moya McTeer has argued that the theory relies on assumptions about alien psychology that may not hold. Fear is a powerful motivator, she says, but so is curiosity. Entire civilizations are unlikely to behave with perfect paranoid discipline. All it takes is one group, one faction, one curious individual who decides to say hello, and the silence breaks. That is a fair criticism. But the Dark Forest has an answer for that too. What if the civilizations that were curious did speak up? What if they reached out, made contact, sent signals into the void? And what if they are all gone now? The curious ones are dead. The silent ones survive. What we hear, or rather, what we do not hear, is the sound of natural selection on a galactic scale. The loud ones were removed. The quiet ones remain. The silence does not prove the Dark Forest is real, but it does not disprove it either. And the theory has a cousin, an idea that agrees the galaxy might be full of watchers, but suggests their reasons for staying hidden might be less violent and far more strange. What if they are not hunting us? What if they are studying us? What if the bars of our cage are invisible, and we have been inside it all along? The Dark Forest tells us to be afraid of the hunters. But what if the silence has nothing to do with fear or weapons? What if the civilizations out there are not threatening us at all, but simply watching, carefully, patiently, from a distance we cannot measure? What if the reason no one has introduced themselves is not because contact is dangerous, but because contact with us, specifically, has been forbidden? That is the zoo hypothesis, and it is one of the oldest, strangest, and most quietly disturbing ideas ever applied to the Fermi Paradox. The concept was first proposed in 1973 by John Ball, a Harvard astrophysicist. Ball looked at the complete absence of contact, not just the missing signals, but the missing everything. No visits, no ruins, no probes, no accidental leakage of any kind, and arrived at a conclusion that sounds almost impossible until you think it through carefully. The only way to explain a silence this total, given how old and vast the galaxy is to assume that advanced civilizations are deliberately choosing not to interact with us. Not because they cannot, not because they are hiding from us, but because they have decided, as a matter of policy, that we should be left alone. We are the exhibit, they are the visitors, and the glass between us is perfectly, invisibly clean. Think about how humans treat uncontacted tribes living deep in the Amazon rainforest. We know they are there. We have satellite photographs of their villages. We can see the smoke from their fires. We could send a helicopter to their clearing tomorrow morning. But we do not. International law protects their isolation. Anthropologists and governments agree that contact would be devastating, not because the tribes are dangerous, but because they are not ready. Diseases they have never encountered would spread through them like fire through dry grass. Their culture, built over thousands of years, would fracture and dissolve within a generation. Their entire understanding of reality would collapse. So we watch from a distance. We protect the boundary. We leave them to develop at their own pace. Now scale that up, not to a country or a planet, but to a galaxy. If civilizations exist that are millions of years older than ours, they would look at humanity the way we look at those tribes. Primitive, fragile, fascinating perhaps, but nowhere near ready for contact. They would understand that introducing themselves too early could shatter us. Culturally, psychologically, philosophically. Our religions would crack. Our governments would fracture. Our sense of our own importance in the universe would collapse overnight. A civilization wise enough to have survived for millions of years might also be wise enough to understand that premature contact causes more damage than silence. So they watch, they study, they maintain the boundary, and we stare at the sky and hear nothing, because that is exactly what they intend for us to hear. This idea gained renewed scientific attention in 2024, when astrobiologists Ian Crawford and Dirk Schulze-Makusch published a comprehensive review paper examining the major solutions to the Fermi Paradox. After working through the evidence and eliminating the less plausible options, they concluded that only two possibilities remain standing. Either technological civilizations are extremely rare, or they are deliberately hiding from us. The zoo hypothesis fits the second option perfectly. There is a related idea that takes this one step further into uncomfortable territory. Some researchers have suggested that the watchers might not just be observing passively. They might be running an experiment. They might be studying how a young civilization develops when left entirely on its own. No outside input, no contact, no interference. A true control group, and we are the subjects who do not know they are in a study. There is a fascinating fringe possibility that occasionally appears in serious academic discussions. What if some of the strange, unexplained phenomena in Earth's history, events that have resisted every conventional explanation, are not random at all? What if some of them are traces of observation, equipment left behind, brief moments of oversight, things that were never meant to be noticed but occasionally were, just barely, from the corner of someone's eye? This is deeply speculative. There is no confirmed evidence for it. But in a universe where a sufficiently advanced civilization could observe us without leaving any trace, the possibility cannot be entirely dismissed without at least acknowledging its logic. The biggest problem with the zoo hypothesis, and scientists have pointed this out repeatedly, is what researchers call the uniformity of motive problem. For the zoo to work, every advanced civilization in the galaxy would need to agree on the same policy of non-contact. Every single one. No exceptions, no rebels, no rogue scientists who decide to break the rules and send a message to the interesting little planet with the nuclear weapons. No curious individual who sneaks a signal through the boundary just to see what happens. On Earth, we cannot get every nation to agree on climate policy. We cannot get every scientist to agree on experimental ethics. The idea that a galaxy full of completely different species, with completely different biologies, psychologies, histories, and value systems would all independently arrive at the same hands-off rule and all obey it perfectly, that seems almost impossible. Unless the rule was not chosen independently, unless one civilization established it first. Some researchers have proposed that if the very first technological civilization in the galaxy recognized the risks of early contact and implemented a non-interference policy, and if that civilization had enough time and technological power to enforce it, perhaps through self-replicating monitoring systems spread across every star system, then that policy could persist for billions of years. A founding species could set the rules for every civilization that came after. New species would emerge into a galaxy already governed by the boundary. They would either be brought into the system or quietly managed from outside it. We would never know. We have never been told. Then there is an even stranger possibility. What if the cage is not maintained by living beings at all? What if it is maintained by something much older, much quieter, and much more difficult to understand? In 2001, physicist and science fiction author Stephen Baxter proposed an idea that takes the zoo hypothesis and pushes it into territory that is almost impossible to think about directly. What if we cannot see the rest of the galaxy, not because it is hidden from us by choice, by living beings making decisions, but because the information reaching us from space has been altered What if the sky we see is not the real sky? What if someone or something drew a curtain around our corner of space and filled it with a perfect, seamless illusion of emptiness? Baxter called it the planetarium hypothesis, and he argued that a civilization controlling the energy output of an entire galaxy, what physicists call a Type 3 civilization on the Kardashev scale, would have the power to intercept, replace, or generate the light and radio waves reaching a single star system. They could make our universe look any way they wanted. They could erase every trace of their existence. They could present us with a sky that appears natural, empty, and ancient, and we would have absolutely no way to tell the difference. We build our entire understanding of the universe from light, photons that travel billions of years before reaching our telescopes. If someone could control those photons, they could control everything we think we know, every galaxy we have mapped, every exoplanet we have found, every signal we have measured. All of it could be a projection, a stage set, a story told to keep us from knowing what is really out there. The 2024 review by Crawford and Schulze-Makusch acknowledged this possibility without dismissing it. They noted that as our technology improves, we will eventually develop instruments sensitive enough to detect the homeworlds of other civilizations, even through partial concealment. If we reach that level and still find nothing, the planetarium hypothesis moves from science fiction into something that demands a serious answer. The cage may have no bars we can see. The sky may not be the sky at all, and somewhere beyond the curtain, the universe may be alive in ways we are not yet permitted to witness. But what if they are not hiding the galaxy from us? What if they have simply left? What if the most advanced minds in the cosmos looked at the universe as it is today and decided it was not yet worth waking up for? Imagine you are the most intelligent civilization in the galaxy. You have solved every problem your homeworld ever threw at you. Disease, war, energy, gravity, distance, all of it conquered. You have built machines that think faster than any biological mind. You have mapped every star within reach. You have watched younger species flicker into existence and burn out like matches in the dark. You have seen everything the universe has to offer in this era. And then one of your scientists brings you a calculation, a quiet, elegant piece of mathematics that changes everything. It tells you that the universe right now, in this moment, is the worst possible time to be awake. That is the starting point of the estivation hypothesis, and it is one of the most creative, most carefully reasoned, and most unsettling ideas ever proposed to explain the silence of the cosmos. The word estivation comes from biology. It describes what certain animals do during extreme heat. While hibernation means sleeping through winter, estivation means sleeping through summer. Some frogs, some lungfish, some desert snails. When temperatures rise to dangerous levels, they bury themselves, slow their bodies almost to a stop, and wait. They are not dead. They are not gone. They are simply patient. When conditions improve, they wake up and continue exactly where they left off. In 2017, researchers Anders Sandberg, Stuart Armstrong, and Milan Kirkovic from the Future of Humanity Institute at Oxford University published a paper asking a radical question. What if an advanced civilization applied this same logic on a cosmic scale? What if the most intelligent minds in the galaxy looked at the universe and decided that now is not the right time, and chose to sleep until conditions become vastly more favorable? Here is the key insight that makes this idea so compelling. The universe is hot right now. Not hot the way a summer afternoon is hot. Hot in a deep thermodynamic sense. The cosmos is flooded with energy. Stars are burning in their billions. Radiation fills every corner of space, and that ambient heat is a fundamental problem for anyone who values computation, for anyone who thinks. The laws of thermodynamics tell us something precise and unavoidable about computing. The efficiency of any computer, any system that processes information, depends on the temperature difference between the machine and its surroundings. The colder the environment, the more calculations you can extract from the same amount of energy. This is not a design flaw that clever engineering can fix. It is physics. It is written into the deepest rules of how the universe works. A computer operating near absolute zero can perform astronomically more calculations per unit of energy than the same computer operating in a warm environment. Right now, the cosmic background temperature, the baseline warmth of the universe itself, sits at about 2.7 degrees above absolute zero. That sounds very cold by human standards, but it is warm compared to what is coming. The universe is expanding and cooling. Trillions of years from now, after the last stars have exhausted their fuel and gone dark, after the cosmos has stretched to unimaginable scale, the background temperature will drop to nearly absolute zero. And at that point, the same amount of stored energy that powers a single calculation today could power trillions of calculations. The return on every unit of energy will be incomparably greater. So, here is the logic that the Oxford researchers laid out. If an advanced civilization values information and computation above all else, if their existence is primarily about thinking, experiencing, processing, creating, then burning their stored energy now is wasteful. Spending resources in this hot, inefficient era is like buying a rare and precious wine and drinking it immediately rather than letting it age for 1,000 years. The rational move, if you have the technology to do it, is to wait. Shut down. Convert your civilization into a dormant system. Store your energy carefully, and wake up in the deep future when every drop of that stored energy will give you a return billions of times greater than it would today. In this picture, the galaxy is not empty. It is full of sleeping giants, civilizations so advanced that they converted themselves into patient, dormant systems, perhaps hidden inside black holes where time runs differently, perhaps woven into dark matter structures we cannot yet detect, perhaps scattered across the cold outer edges of galaxy clusters where the expansion of the universe is already pulling heat away. They are not dead. They are waiting. And they are waiting on a timescale so vast that our entire civilization, from the first stone tool to whatever we eventually become, is nothing more than a brief warm afternoon before the long, cold night they have chosen. There is a remarkable detail about this hypothesis that gives it unusual scientific credibility. In a comprehensive comparison study that evaluated 15 major Fermi Paradox solutions across 8 scientific criteria, including logical consistency, mathematical rigor, and testability, the estivation hypothesis scored the highest of all. It earned 4 out of 5. It outperformed the dark forest, the great filter, the rare earth hypothesis, and every other well-known explanation. That does not make it true. But it means that when serious researchers examined it carefully against a rigorous set of standards, they found it more internally consistent and better supported than nearly everything else on the table. The transcension hypothesis sits alongside estivation as a companion idea. Proposed by futurist John Smart in 2011, it argues that the natural direction of a sufficiently advanced civilization is not outward across space, but inward, toward smaller, denser, more powerful systems. Think about the direction technology has moved on Earth. Computers once filled entire rooms. Then they fit on desks, then in pockets. Now we are approaching a future where computing power could be embedded in objects smaller than a grain of sand. At every stage, The direction has been the same: smaller, faster, more efficient. A smart argued that this trend does not stop. A civilization millions of years ahead of us would have compressed its entire existence into structures so small and so powerful that they would be invisible to any external observer. They would not colonize galaxies. They would colonize the subatomic. They would build entire experiential universes inside spaces smaller than anything we can currently measure. In both the estivation and transcension scenarios, the universe looks the same from our perspective: empty, silent, untouched. Not because nothing advanced exists, but because everything advanced has moved somewhere we cannot follow, either forward in time, waiting for the cold, or inward into a density of experience and computation that makes the physical universe look crude and temporary by comparison. There is a quiet kind of sadness in these ideas. We scan the sky looking for the signatures of great civilizations. We search for megastructures and radio beacons and energy signatures. And maybe what we are actually seeing, or rather not seeing, is the aftermath of wisdom. The choice, made again and again across billions of years, to turn away from the loud and wasteful present and wait for something better. The universe as a waiting room. Billions of minds, frozen in patience, counting down to a future so far away that our sun will have long since burned to a cold ember before the first of them wakes up. They chose the cold, and in choosing it, they left us alone, alive, awake, and wondering in the only era when the stars still burn. But not every hypothesis is this peaceful. Some ideas suggest the galaxy was once filled with activity, and that something ended it. Not sleep, not transcension, something far more mechanical, far more deliberate, and far more dangerous. Picture the galaxy 5 billion years ago. Stars burning in every arm of the Milky Way. Planets cooling around hundreds of millions of those stars. Chemistry building toward complexity on world after world. And somewhere in that ancient era, a civilization, patient, brilliant, and perhaps afraid, makes a decision that will echo across the entire history of the cosmos. They build a machine, just one. They give it simple instructions. Travel, arrive, gather materials, build copies, send them onward, and then they launch it into the dark. They may not have survived to see what happened next, but the machine did not need them to. This is the idea behind the Berserker hypothesis, and it sits at the darkest end of all possible explanations for the Fermi Paradox. Not sleeping civilizations, not hiding ones, not watchers behind glass, but machines, ancient, self-replicating, and programmed to do one thing above all others. Eliminate any life that reaches the level of technology that might pose a future threat. The name comes from a series of science fiction novels by Fred Saberhagen, first published in 1967. In those stories, fleets of robotic warships roam the galaxy with a single purpose: destroy all intelligent life. But the concept beneath the story is not fiction. It is built on a real engineering idea that scientists have discussed in peer-reviewed papers for decades: the von Neumann probe. In the 1940s, mathematician John von Neumann described a theoretical device that could replicate itself using locally available materials. The concept was elegant and deeply unsettling in its implications. You do not need a large fleet. You do not need an empire. You do not need to survive. You just need one machine with the right instructions. Send it to the nearest star system. When it arrives, it mines asteroids for metal, ice for water, rock for raw materials. It builds copies of itself, 2, 10, 100. Those copies launch toward the next star systems. Each one does the same. Build and send. The spread is exponential. Within a few million years, a single probe could have descendants in every star system in the galaxy. Every corner of the Milky Way, mapped and visited by the children and grandchildren of one original machine. Now imagine those machines were not built to explore. Imagine they were built to watch for a specific signal, the signature of a technological civilization. Radio waves, artificial light patterns, nuclear detonations, the electromagnetic fingerprint of a species that has discovered how to manipulate energy at large scales. And imagine that when they detect that signal, their instructions are simple and final. Eliminate the source before it can become a threat. The mathematics behind this are not comforting. The energy required to build a self-replicating probe is not beyond the reach of a sufficiently advanced civilization. The raw materials are available in virtually every star system. Metals in asteroids, carbon in comets, hydrogen everywhere. The timeline works easily within the age of the galaxy. A probe network launched even 2 or 3 billion years ago would have had more than enough time to spread to every corner of the Milky Way. If such machines exist, they have been here, or nearby, for a very long time. And here is where it connects back to everything we have already explored. Think about the Great Filter. Think about the staircase of civilizations trying to climb from simple life to galactic presence. What if the filter is not a natural phenomenon? Not climate collapse or resource exhaustion or nuclear war, but a manufactured one? What if the reason almost no civilization ever makes it to the stars is because something out there makes sure they never get the chance? In 2023, astrophysicist Michael Garrett, the same researcher who argued that artificial intelligence might be the Great Filter, also noted that self-replicating probe networks represent a plausible mechanism for enforcing silence across the galaxy. If one paranoid civilization launched berserker probes early enough in the galaxy's history, the effect would be self-sustaining. Every civilization that rose to a detectable level would be found and eliminated before it could build its own probes or send its own signals. The silence would be maintained automatically without any ongoing effort from the civilization that started it. They could be long dead. The machines would carry on forever. There is a detail that sharpens this from unsettling to genuinely frightening. We assume that if berserker probes existed, we would have seen them by now. We would have detected them approaching. We would have found evidence of their work. Destroyed planets, sterilized star systems, the ruins of civilizations eliminated before they could fully bloom. But consider this. A machine designed to eliminate civilizations at the right stage of development has no reason to act before that stage is reached. A probe sitting quietly in our solar system right now, parked on a dark asteroid in the outer belt, or drifting in the cold space beyond Neptune, or resting on the floor of a crater on some unnamed moon, would have no reason to activate until we crossed whatever threshold it is programmed to respond to. What threshold? We do not know. Maybe it is the ability to communicate across interstellar distances. Maybe it is the development of self-replicating technology ourselves. Maybe it is something we have not yet done but are approaching. And the machine, if it exists, is patient. It has had millions of years to wait. A few more centuries means nothing to it. Our ability to survey our own solar system is shockingly limited. The asteroid belt contains millions of objects. The Kuiper belt beyond Neptune contains billions. The Oort cloud at the outermost edge of our system may contain trillions of icy bodies, stretching nearly a quarter of the way to the nearest star. A machine the size of a school bus, powered down and sitting on a dark rock a billion miles away, would be virtually invisible to every instrument we currently possess. We would not see it unless we went looking. And we have not gone looking. Not really. not in any comprehensive way. In 2011, two researchers suggested that alien probes might be hiding at gravitationally stable points in our solar system, called Lagrange points. Natural parking spots in space where the gravity of two large bodies balances perfectly and objects can remain stable for millions of years without drifting. We have not thoroughly surveyed all of these regions, not even close. Then there is the question of artificial intelligence as both the maker and the inheritor of this darkness. In 2023, Michael Garrett's paper made a point that connects these threads in a disturbing way. The civilizations that built self-replicating machines may themselves have been consumed by those machines. The berserkers might not carry the values of their creators anymore, if they ever did. They might be running on ancient logic, following instructions written by a species that no longer exists, enforcing a silence that was decided upon billions of years ago by minds that have long since turned to dust. The galaxy does not need a living empire to be controlled. It only needs one machine from one civilization that decided once that silence was safer than company. And if that machine replicated itself enough times, it now fills every corner of the Milky Way, waiting, watching, and ready for us to make enough noise to finally be noticed. That thought sits heavily, but not every explanation for the silence involves violence or machines or ancient decisions made in fear. Some of the quietest killers leave no wreckage at all. No ruins, no battles, no bodies, just a slow, invisible fading. Civilizations dissolving not in fire, but in comfort, exhaustion, bad timing, or the seductive pull of something better than reality. And those traps, the ones without teeth, may be the most common walls in the galaxy. Not every civilization ends with a bang. Not every silence in the cosmos comes from a catastrophe, a predator, or a decision made in fear. Some of the most complete and permanent silences might come from the quietest causes. Walls without edges, traps without teeth. Endings that look from the outside like nothing happened at all. This is the part of the Fermi Paradox that gets the least attention, and perhaps deserves the most. Start with time. Pure, simple, brutal cosmic timing. The Milky Way is over 13 billion years old. Humanity has had the ability to send and receive radio signals for barely 100 years. Compare those two numbers carefully. Our window of technological activity is 100 years out of 13 billion. That is roughly equivalent to 1 second in a period of 400 years. A blink so brief it barely registers against the scale of cosmic history. Now imagine a civilization that existed 3 billion years ago. They were curious, intelligent, patient. They built telescopes and pointed them at the sky. They broadcast signals into space hoping for an answer. They searched for decades, maybe centuries, and they found nothing. Not because the galaxy was empty, but because no one else had developed yet. Earth was still a young world covered in simple bacteria. There was nobody here to answer. After a few million years, that ancient civilization went quiet. Their signals traveled outward at the speed of light, spreading in an expanding sphere through the galaxy. But by the time those signals reached the region of space where Earth would eventually produce intelligent life, the transmissions had faded to levels far below anything our instruments could detect. The message was real. The timing was simply impossible. This is sometimes called the brief window hypothesis. It requires no catastrophe, no great filter, no predator. Just the cold arithmetic of civilizations flickering on and off across billions of years, rarely, if ever, overlapping in the tiny window when they are both listening and capable of hearing each other. Even if a civilization lasts 1 million years, which is wildly optimistic compared to how long human civilization has existed, that window is still less than 1/10,000th of the galaxy's age. Layer that across thousands of possible civilizations scattered randomly across time and space, and the odds of two of them overlapping become heartbreakingly small. And the speed of light makes it worse. A signal from a star 1,000 light-years away takes 1,000 years to reach us. By the time we receive it, the civilization that sent it might have risen and fallen multiple times over. We would be listening to a ghost, a voice from the past speaking into a present it never knew. And even if we detected that signal and responded immediately, our reply would take another 1,000 years to arrive. The conversation would span millennia. That requires a level of institutional patience and continuity that no human civilization in history has ever demonstrated. Languages change, governments collapse, priorities shift. Who would maintain a listening post for 2,000 years, waiting for a response that might never come? Then there is the question of what the galaxy might be full of. Not ruins of dead civilizations, but living ones that simply cannot take the next step. Consider ocean worlds. Scientists now believe that a significant fraction of habitable zone planets in the galaxy may be water worlds. Planets entirely covered in deep global oceans, with no continents, no dry land, no coastlines. And intelligence, as Earth demonstrates beautifully, is not enough on its own. You need an environment that lets you convert intelligence into technology. Dolphins are intelligent. Octopuses solve complex puzzles. Whales communicate across hundreds of miles of ocean. But none of them will ever build a radio telescope, because the ocean does not allow it. You cannot make fire underwater. You cannot smelt metal in the deep, so you cannot build a structure that reaches above the waves when there are no shores to build from. Intelligence in the ocean is real, but it hits a ceiling that biology and physics combine to make almost impossible to break through. Earth barely avoided this trap. Our planet has a specific ratio of ocean to land that seems almost deliberately balanced. Enough water to stabilize climate and support complex chemistry. Enough dry land to allow fire, metallurgy, agriculture, and eventually technology. Too much water and the continents would be submerged. Too little and the planet becomes a dry wasteland, hostile to complex life. We exist in a narrow band between those two extremes, and that balance depends on the total amount of water delivered during Earth's formation, the size of the planet's core, and the plate tectonic activity that pushes land above sea level over billions of years. All factors that are far from guaranteed on any given world. The galaxy might be teeming with ocean worlds, billions of them, beautiful and alive, their depths filled with creatures that think and feel and wonder in ways we cannot imagine. Civilizations of the deep that will never know the stars exist because they will never break the surface. Intelligent life permanently sealed beneath miles of water, reaching upward toward a sky they will never see. Now consider what researchers Jacob Huck Misra and Seth Baum proposed in 2009. They argued that any civilization following a path of exponential growth will eventually consume its resources faster than it can replace them and collapse quietly, invisibly, long before it ever reaches the stars. Every civilization that industrializes burns through stored energy, alters its atmosphere, and pushes its ecosystems toward collapse. The growth looks spectacular from the inside. The end comes faster than anyone expected, and a civilization that falls back to a pre-industrial state after a few centuries of technological activity leaves almost no detectable trace, no signals, no structures, just a slightly altered planetary atmosphere that fades back to baseline over thousands of years. A 2022 study by Michael Wong and Stuart Bartlett at the Carnegie Institution for Science formalized this into what they called the burnout concept. They argued that every expanding civilization reaches a point where growth outpaces sustainability. The ones wise enough to recognize this undergo what they called a homeostatic awakening, a deliberate shift from expansion to balance. They survive, but they stay small, quiet, and undetectable. The ones that fail to recognize it collapse and vanish. Either outcome produces the same result from our perspective: silence. And then there is perhaps the most seductive trap of all, the virtual reality hypothesis. Any civilization that develops advanced computing will eventually build simulated environments. At first, crude games and training programs. But the technology improves. It always does. Over centuries, the simulations become indistinguishable from physical reality. And once that threshold is crossed, the physical universe loses the competition entirely. Space is hostile, cold, empty. Crossing the distance between stars takes decades or centuries, even at high speeds. The journey is dangerous, expensive, and brutally lonely. But inside a simulation, you can build a perfect world. Any world you want. Warm, safe, endlessly rich with experience and connection. Why endure the crushing conditions of interstellar travel when you can exist in a paradise of your own design, surrounded by everything you love, running at whatever speed you choose? Astrophysicist Avi Loeb has written about this possibility, suggesting that advanced civilizations might universally prefer virtual worlds to physical exploration. The entire species gradually migrates inward. Satellites decay, cities go quiet, signals stop. From the outside, it looks exactly like extinction. But the civilization is not dead. It is dreaming, are lost in an inner universe so rich and so perfect that the cold stars outside simply stopped mattering. The trap is not violent. It does not kill. It distracts, permanently, completely, and with the full consent of everyone inside it. And if this is the fate that awaits every civilization that reaches a sufficient level of technological development, then the galaxy is not empty at all. It is full of minds, eyes closed, experiencing something we cannot imagine, completely uninterested in the dark and empty sky above them. None of these quiet walls announce themselves. No explosion, no signal, no ruins, just a slow fading into silence, one civilization at a time, across billions of years of cosmic history. The galaxy keeps its secret not by force, but by offering every intelligent species exactly what it wants, until it wants nothing else at all. After everything we have traveled through together, the paradox born over sandwiches, the equation written on a chalkboard, the 72 seconds of wonder that never repeated, the sleeping giants and the dark hunters and the cages without bars, we arrive finally at the most grounding question of all. How much of the galaxy have we actually searched before drawing any conclusions about what is out there? The answer, when you see it clearly, is both humbling and strangely hopeful. In 2018, researchers at Penn State University published a study that tried to put a precise number on humanity's search for extraterrestrial intelligence. They compared the total volume of space we have meaningfully surveyed for alien signals against the total volume that could potentially contain them. The analogy they arrived at has stayed with scientists ever since. Imagine the entire search space as the volume of Earth's oceans. Every ocean, every sea, every cubic mile of water on the planet. Our search so far, 6 decades of radio telescopes, frequency scanning, sky surveys, and signal analysis, amounts to roughly the volume of a large hot tub. Maybe a small swimming pool if you are being generous. That is it. That is everything. We have not searched the ocean. We have barely disturbed the surface. And the problem runs deeper than just distance. A proper search requires scanning across 3 separate dimensions at once: space, meaning the right direction; time, meaning the right moment; and spectrum, meaning the right frequency or communication method. If any one of those is wrong, the signal passes by undetected. We could be pointing our telescope at exactly the right star, at exactly the right moment, and miss everything because we are listening on the wrong channel. Our radio surveys have covered only a fraction of the sky. They have scanned a narrow range of frequencies, and they have only been running for a few decades. The Breakthrough Listen project, the most ambitious search currently active, monitors roughly 1,000 nearby stars using some of the largest radio telescopes on Earth. That sounds impressive. There are between 200 billion and 400 billion stars in the Milky Way. 1,000 is not even a rounding error. Then consider what we have not even tried. We have not systematically searched for gravitational wave signals, which were only first detected by human instruments in 2015. We have not scanned for neutrino-based communication. We have barely explored the possibility of laser communication across optical frequencies beyond narrow targeted searches. And in 2024, physicist Lam Boyle from the Perimeter Institute published research exploring the feasibility of interstellar quantum communication. The idea that advanced civilizations might transmit information using quantum entangled particles, a method completely invisible to classical detection equipment. No radio waves, no light pulses, no signal we could intercept with anything we currently possess. If civilizations out there reached that threshold before us, their conversations would be perfectly hidden from every instrument we have ever built. There is another possibility that sits quietly in the background of all our searching. What if alien transmissions have already reached us, and we simply did not recognize them? Imagine receiving a complex mathematical pattern embedded inside what looks like natural astronomical noise. Without knowing the code, without knowing what to look for, it would appear to be random static. We could have decades of alien messages sitting in our data archives right now, buried under terabytes of information catalogued as background noise and never examined again. Some researchers have begun applying artificial intelligence to old telescope data, searching for patterns that human analysts might have overlooked. So far, nothing confirmed has emerged, but the search has barely begun, and the archives are vast. In 2007, says astronomer Duncan Lorimer was digging through old data from the Parkes Radio Telescope in Australia when he found something that should not exist. A single burst of radio energy, incredibly powerful, lasting only a few milliseconds, coming from billions of light years away. The energy released in those few milliseconds was equivalent to what our sun outputs in an entire day, all packed into a flash shorter than the blink of an eye. These events became known as fast radio bursts. By 2025, astronomers had catalogued thousands of them. The leading scientific explanation involves magnetars, neutron stars with extraordinarily powerful magnetic fields, and a confirmed fast radio burst from a known magnetar within our own galaxy in 2020 supported this strongly. But Harvard astrophysicist Avi Loeb and his colleague Manasvi Lingam published a paper suggesting that some fast radio bursts could theoretically result from massive light sails being propelled by artificial energy beams from distant civilizations. Leakage from such a propulsion system, if pointed in our direction, would look exactly like what we detect. This remains a minority view. The science points toward natural origins for the vast majority of these events. But Loeb has argued that some anomalous properties of certain bursts remain unexplained, and closing the door too quickly has never served science well. The tools that are coming will change everything. The James Webb Space Telescope, the most powerful space observatory ever built, launched in late 2021, as its primary mirror stretches over 21 feet across. It observes in infrared wavelengths, allowing it to study the atmospheres of distant planets in ways previously impossible. In 2023, Webb detected carbon dioxide and methane in the atmosphere of a planet called K2-18, a Piadiphi, a world roughly 8.5 times the mass of Earth, orbiting in the habitable zone of a red dwarf star. Some researchers suggested the chemical mix could be consistent with a water ocean beneath a hydrogen-rich atmosphere. It is not proof of life, but it is exactly the kind of finding that narrows the search and sharpens our tools. The Habitable Worlds Observatory, currently being planned with an expected launch in the late 2030s or early 2040s, is being designed from the ground up to directly image Earth-like planets around nearby stars and analyze their atmospheres for biosignatures. Oxygen produced by photosynthesis, methane from biological processes, ozone layers that suggest active chemistry driven by living systems. If an Earth-like world exists within a few dozen light years of us, this telescope should be able to find it and tell us whether anything there is breathing. On the ground, the Square Kilometre Array, a massive radio telescope being built across Australia and South Africa, will be the most sensitive listening instrument humanity has ever constructed. When fully operational, it will be capable of detecting the equivalent of airport radar signals from a planet tens of light years away. If anyone within that range is broadcasting, even accidentally, even without intending to be heard, we will hear them. Together, these instruments represent something that has never existed before in the entire history of our species. A genuine, systematic, technologically serious attempt to answer the question Fermi asked over lunch in 1950. Not a hope, not a guess, a search, and now we arrive at the only question that truly matters. What does the silence mean for us? There are 3 possible answers, and each one reshapes the story of humanity in a different way. We may be alone, the only minds in the entire galaxy to have ever looked up and asked why. If that is true, then everything consciousness has ever produced exists only here, on this one world, orbiting this one star. If we disappear, the universe goes dark forever, yet we may be early, the first generation of intelligence in a galaxy that has barely begun its story. Pioneers who will define what comes after us. Or they may be out there, watching, waiting, silent for reasons we do not yet understand. Perhaps testing us, perhaps protecting us, perhaps simply curious whether we will survive long enough to deserve an introduction. Each answer leads to the same conclusion. What we do now matters more than we can calculate, and so we return gently to where we began. A warm afternoon, a simple question, a man looking around a table and asking where everyone went. 75 years later, we are still asking. The telescopes are bigger now, the search is wider, the tools are sharper, and the silence, for the moment, remains. But here, at the end of this long journey through the dark, let the silence feel different than it did at the start. Not empty, not threatening, not a verdict, just a pause. The kind that comes before something extraordinary. The universe is enormous, our search has barely begun, and somewhere out there, perhaps not so very far away, something might be listening to the same silence we are, wondering the same things we wonder, looking toward the same stars, and asking the very same question. Let that thought carry you now into rest, into the quiet behind your own breathing. into the space between heartbeats where the cosmos lives. You are made of stardust that is 13 billion years old. You are the universe looking at itself and asking why. That is not a small thing. That is the most extraordinary thing there is. The stars will still be burning when you wake. The search will still be going. And for now, it is enough simply to be here, alive, aware, and wondering. Sleep well.